Thank you for following us on Nancy Guthrie's scary case, and what we are about to share with you tonight is going to completely change the way you see this investigation. The story unfolding behind the scenes is not the story of a stalled investigation hitting a dead end. It is the story of a technological war being fought at the molecular level, a war so sophisticated, so breathtaking in its scientific ambition, and so deeply unsettling in its implications that the person who walked into Nancy Guthrie's home and took her from her family may have absolutely no idea that the very cells they shed without thinking, the hairs they lost without noticing, the microscopic biological traces they left behind without a second thought, are right now being decoded by some of the most powerful forensic technology ever developed by human beings. The walls they believed they had built around their identity are being dismantled, one genetic data point at a time, by a science so new and so powerful that most people have never heard of it, and most criminals have no framework for understanding the threat it poses to them. And the woman at the center of that technological war, the person whose name makes cold case perpetrators nervous, and whose methodology has already reached through decades of silence to unmask more than 250 criminals, who were absolutely certain they had gotten away with it, is C.C. Moore. If you are new here, welcome to True Crime Hex. Hit that subscribe button and ring that notification bell right now, because this is exactly the kind of deep, science-forward, expert-level analysis we bring you every single week on this channel. And you do not want to miss a single update on this case, or any of the extraordinary cases we cover here. And tonight, we are going all the way inside one of the most fascinating and frustrating forensic puzzles in recent memory. Now, let us talk about the wall. The DNA was there. It was sitting right there on that door handle, a microscopic confession written in the most intimate biological language known to science, the very language of identity itself, the molecular record of a specific human being who was present in that home on the night Nancy Guthrie disappeared. And it means almost nothing. For more than 2 months, the single most promising piece of physical evidence recovered from the scene of Nancy Guthrie's abduction has been sitting in a forensic laboratory. And instead of unlocking this investigation, instead of pointing a decisive and unambiguous finger at the person responsible for shattering the lives of an entire family and plunging an entire community into fear, it has done the precise and maddening opposite. It has created a puzzle so complex, so deeply layered with competing genetic signals and overwhelming biological noise, so resistant to every conventional analytical approach that has been thrown at it, that the finest forensic minds available to the Pima County Sheriff's Department have been brought to a complete and agonizing standstill. The investigation into the disappearance of an 84-year-old woman, a grandmother, a retired librarian, a quiet and beloved cornerstone of her community, has been functionally paralyzed by the very evidence that was supposed to set it free and give her family the answers they are desperately waiting for. Think about what that means for a moment, and sit with the full weight of it. We live in an era where we have been told repeatedly, emphatically, and with enormous cultural confidence that DNA evidence is the gold standard of criminal investigation. It is the final word. It is the courtroom trump card, the prosecutorial ace, the scientific argument ender that no defense attorney can credibly challenge and no jury can easily dismiss. When eyewitness testimony has crumbled under cross-examination and alibis have fallen apart and surveillance footage has been too grainy to be definitive, DNA has been the last, unimpeachable voice of truth, standing in the silence. Jurors trust it implicitly. Judges assign it enormous weight. Television built entire primetime franchises on it. The true crime industry built its podcasting empire on it. We as a society have placed our collective faith in the molecular architecture of life itself as the ultimate arbiter of guilt and innocence, the one piece of evidence that cannot lie and cannot be argued away. And now, here we are. A woman is missing. A family is living through an anguish that most of us will, thankfully, never comprehend. A perpetrator is walking free, somewhere out there in the sun-baked streets and subdivisions of Tucson, Arizona, breathing clean desert air and living their life as though nothing happened, as though they did not walk into the home of an elderly woman and take her from the family that loves her. And the DNA that was left at the scene, this supposed gold standard, this final word, this unimpeachable molecular truth, is speaking in riddles so dense and so convoluted and so resistant to conventional interpretation that investigators are, for all practical purposes, no closer to a public breakthrough today than they were on the morning Nancy Guthrie disappeared. The gold standard has revealed itself, in this specific and devastating instance, to be something far more complicated than the television dramas ever suggested. It has revealed itself to be a genetic puzzle that mocks conventional forensic methodology with every failed attempt to decipher it. But here is what the official silence does not tell you. Here is what the carefully worded press releases, and the measured statements from law enforcement deliberately, and, perhaps necessarily, obscure, because they cannot reveal the details of an active investigation without potentially compromising the very methods they are using to pursue it. The silence is not inaction. The silence is not defeat. The silence is not the sound of investigators staring helplessly at an insurmountable wall with no idea how to climb it or go around it or tear it down. If you know how to listen to it, and Cece Moore knows exactly how to listen to it because she has heard this particular silence before in dozens of investigations that eventually broke wide open, the silence is the most furious and focused kind of work imaginable. It is the sound of a scientific paradigm shift happening in real time. It is the quiet hum of laboratory servers processing tens of millions of genetic simulations simultaneously. It is the sound of ancient DNA chemistry developed to read the genomes of creatures dead for 40,000 years, being applied to a single hair shaft found in the home of a missing 84-year-old woman in Tucson. It is the focused and relentless click of a genetic genealogist's mouse tracing a family line backward through census records and marriage licenses and obituaries and church records to the 1800s, looking for the ancestral thread that connects a distant database match to the phantom who walked out of Nancy Guthrie's home and vanished. And it could, at any moment, and with no advance warning to the public, break this entire case wide open in a way that no conventional investigative method ever could. Cece Moore is the chief genetic genealogist at Parabon Nanolabs, and she is the person you call when the DNA is the only witness left, and even that witness is barely whispering through a wall of genetic noise. She pioneered the use of public genealogy databases to identify criminal suspects, developed the systematic methodologies now used by law enforcement agencies across the United States and internationally, and produced the first-ever criminal conviction in the history of the legal system where the suspect was identified exclusively through investigative genetic genealogy, a milestone that validated the entire field and permanently altered the landscape of what is possible in criminal investigation. She has personally contributed to solving more than 250 cases. She has reached back through decades of silence and pulled out names that law enforcement had given up on ever finding. She understands the exact kind of forensic nightmare that is stalling this investigation with an intimacy born of repeated direct experience. She has faced scenarios like this before and overcome them. And she knows the specific weapons in the technological arsenal that investigators are almost certainly deploying right now in the laboratories and on the workstations that are humming quietly behind the wall of official silence surrounding the search for Nancy Guthrie. While she is not officially working on this case, her expertise gives us an unprecedented and genuinely remarkable window into what is actually happening beneath the surface of this investigation. And what is happening is nothing short of extraordinary. So let us start where the investigation started, and where it has, for now, gotten stuck. Let us start with the evidence. And to understand why the evidence is such a problem, you first need to understand what good DNA evidence actually looks like. Because the contrast between what investigators have and what they need is the key to understanding everything that comes next. Standard forensic DNA analysis is built on a technology called short tandem repeat analysis, universally known by its acronym STR. The human genome is approximately 3 billion base pairs long, an almost incomprehensibly vast genetic landscape, and we share roughly 99.9% of our DNA with every other human being on the planet. That remarkable fact means that all of human biological diversity, every difference in appearance and health and ancestry that we can observe in the world around us, is encoded in a fraction of a percent of our genetic material. The forensic relevance lies in that remaining fraction, and more specifically in particular regions of the genome that are known to vary significantly from person to person in ways that are measurable, reproducible, and statistically extraordinary in their power to distinguish individuals from one another. These regions are called short tandem repeats because they consist of short DNA sequences, typically 2 to 7 base pairs in length, that repeat themselves a variable number of times at specific, known locations throughout the genome. Think of a specific DNA sequence as a word, and the short tandem repeat as the number of times that word appears consecutively in a sentence. In one person, the word might repeat 4 times. In another person at the same location in the genome, it might repeat 11 times. In a third person, 17 times. The number of repeats at each location is inherited, 1 copy from the mother and 1 copy from the father, and the combination of repeat counts across multiple genomic locations creates a profile that is, for all practical statistical purposes, unique to each individual on Earth. The statistical probability of 2 unrelated individuals sharing identical STR profiles across all 20 locations used by the current national standard is so vanishingly small that it is treated, for all legal purposes, as impossible. The current standard for forensic DNA profiling in the United States, the system underlying the national CODIS database that law enforcement relies on for suspect identification, uses 20 specific STR locations, or loci, across the genome. At each locus, a forensic sample from a single individual will produce either 1 peak on the analytical graph if both inherited copies of that chromosome segment happen to have the same repeat count, or 2 distinct and clearly separated peaks, representing the maternal and paternal copies respectively. 20 loci, 1 or 2 peaks each. A clean, unambiguous, visually interpretable genetic fingerprint that can be entered into CODIS and compared against every profile in the national database with extraordinary speed and extraordinary precision. When a match is found, the statistical weight behind it is overwhelming. This is DNA evidence at its best. This is forensic science working exactly as it was designed to work, delivering answers with the kind of clarity and certainty that every investigator and every victim's family hopes for. The real world, however, does not consistently cooperate with the textbook, and a residential door handle in a family home is among the most contamination-prone surfaces that exists anywhere in the forensic universe. Consider for a moment every person who touched Nancy Guthrie's bedroom door handle in the weeks and months before she disappeared. Nancy herself touched it every single day, likely multiple times a day, leaving behind a consistent and substantial deposit of her own cellular material each time. Her children touched it when they came to visit, which they did regularly because she was their mother, and they loved her. Her grandchildren touched it, because children touch everything and leave traces of themselves on every surface they encounter. Perhaps a neighbor who stopped by to check on her touched it. Perhaps a home health aide, or a cleaning service, or a friend who delivered a meal touched it. Each of these innocent, ordinary, completely unremarkable human contacts deposited an invisible layer of cellular material on that surface, a microscopic record of human presence that accumulated over time without anyone's awareness or intention. And then the intruder came, and they touched it too, and they left their own DNA layered on top of everyone else's, adding their genetic information to an already crowded and chaotic biological record. The resulting laboratory data that the forensic scientists are working with is not the clean, elegant set of 1 or 2 peaks per locus that makes standard STR analysis so powerful and reliable. For each of the 20 STR locations, the analytical graph shows not 1 or 2 peaks, but potentially 3, 4, 5, 6 or more peaks of wildly varying heights, representing the overlapping and intermingled genetic contributions of multiple people who had no connection to each other and no awareness that their DNA was being deposited together on the same small surface in the same household. The very first challenge confronting a forensic analyst working with this kind of sample is simply determining how many people contributed to it, because the answer to that question fundamentally changes every subsequent analytical decision and strategy. 2 contributors? 3? 4? 5? Or more? The more contributors present in the sample, the more exponentially complex the mathematical problem of separating and identifying the individual profiles becomes. And there is no clean, algorithmic, objectively determinable method for establishing contributor number with certainty. It is, at its foundation, a professional judgment call, an educated inference based on analytical experience and the statistical properties of the data. And different analysts with different levels of experience and different institutional frameworks can and do reach genuinely different conclusions from the same raw data. This subjectivity in one of the most foundational decisions in complex mixture interpretation is one of several reasons why this area of forensic science has been the subject of significant scientific debate, methodological controversy, and occasional courtroom challenge over the past decade. And the intruder's contribution to this already chaotic sample, according to investigative reporting on the Nancy Guthrie case, may be the smallest and most elusive signal of all. Some reporting has suggested the suspect's DNA may represent as little as 10 to 15% of the total genetic material present in the sample. Pause for a moment and let that sink in. That means for every single molecule of the intruder's genetic material present on that door handle, there are 6 to 9 molecules from entirely innocent individuals drowning it out, overwhelming it, burying it beneath a mountain of irrelevant but indistinguishable biological noise. At that contributor ratio, a phenomenon that forensic scientists call allelic dropout becomes not just a theoretical concern, but a potentially case-defining obstacle. Allelic dropout occurs when a contributor's genetic signal is so weak and so diluted that one or both of their peaks at a given STR locus simply fail to appear in the data at all, disappearing below the threshold of detection as though they were never there. The intruder's genetic whisper is being drowned out not just by the combined noise of every other contributor, but by the fundamental physics and chemistry of the analytical process itself, which requires a minimum quantity of target DNA to reliably amplify and detect a signal. The result is a profile that may be missing not just a few marginal data points, but entire critical sections of the genetic fingerprint, a jigsaw puzzle where the pieces belonging to the one person who matters most to the investigation are the ones that keep coming up absent. Trying to build a usable, legally defensible DNA profile from this kind of evidence is like trying to identify one specific person's voice in a packed football stadium where every other person is shouting at the top of their lungs, except the voice you need to identify is not shouting. It is barely audible. It keeps cutting out entirely. And when it does whisper, its words are being spoken simultaneously with the words of 6 other people, making it impossible to determine with confidence which sounds belong to the voice you are searching for and which belong to everyone else. This is the wall. This is the specific, documented forensic obstacle that has stopped this investigation in its tracks and kept a family waiting in agony for more than 2 months. And understanding exactly how impenetrable this wall really is, at the level of analytical chemistry and statistical inference and molecular biology, is essential to appreciating just how remarkable the tools being deployed to overcome it truly are. If you are finding this breakdown of forensic science as fascinating as we are, and you want to support this kind of deep-dive investigative journalism, make sure you are subscribed to TrueCrime Hex. Hit that notification bell. We are committed to bringing you the most accurate and detailed analysis possible on cases like Nancy Guthrie's. And your support helps us keep doing this important work. The first weapon in the investigative arsenal against a complex mixture of this kind is probabilistic genotyping software. And it is nothing like the simple pattern-matching algorithms that most people imagine when they think about computer-assisted forensic analysis. The programs at the cutting edge of this technology, most notably STR-Mix, developed by the Institute of Environmental Science and Research in New Zealand in collaboration with the forensic science community, and TrueAllele, developed by the Pittsburgh-based company Cybergenetics, are extraordinarily sophisticated computational engines that represent some of the most advanced applied mathematics being used anywhere in the forensic sciences today. They apply principles of Bayesian statistical inference, detailed mathematical modeling of the biological processes involved in DNA replication and amplification, and population genetics to the specific and extraordinarily demanding problem of mixture deconvolution, which is the technical term for the process of pulling apart the overlapping genetic contributions of multiple individuals from a single mixed sample. What makes these programs fundamentally different from earlier approaches to mixture interpretation is that they do not attempt to arrive at a single definitive answer. They do not declare that a particular profile is definitely present in the mixture and another definitely absent. Instead, they operate on a fundamentally probabilistic framework that acknowledges and rigorously quantifies the uncertainty inherent in the analytical process. They run literally tens of millions of simulations, each simulation representing a possible set of genetic combinations from possible contributors that could have produced the observed laboratory data, and they evaluate the mathematical likelihood of each simulated scenario given everything known about DNA, amplification biology, population genetics, and the specific characteristics of the sample. They model the stochastic or random variation in DNA amplification that causes some peaks to be taller than others, even from the same contributor. They model the stutter artifacts that cause small ghost peaks to appear beside real peaks as a byproduct of the amplification process. They model the allelic dropout that causes weak contributors to disappear partially or entirely from the data. By integrating all of these biological realities into a coherent mathematical framework and running millions of simulations that account for all of them simultaneously, these programs generate a probability distribution, a landscape of possibilities rather than a single answer that can be used to calculate a likelihood ratio for any proposed contributor. Think of it as hyper-advanced audio editing applied to genetic information. Imagine a chaotic audio recording from a crowded party where a dozen conversations are happening simultaneously, voices overlapping and interrupting each other, background noise from music and glasses, and ambient sound creating a wall of interference. Standard audio analysis might tell you that there are multiple voices present, but be unable to distinguish any individual conversation with clarity. Probabilistic genotyping software is like a tool that can listen to that entire chaotic recording, and, by identifying unique acoustic patterns, statistical regularities, and mathematical signatures that belong to specific voices, isolate one particular conversation from all the surrounding noise, and tell you with quantifiable confidence how likely it is that a specific person was the one speaking. Not with absolute certainty, because the uncertainty of the original recording cannot be entirely eliminated, but with a precisely calculated probability that can be expressed as a number and evaluated in a legal context. In the Guthrie case, the software would have been fed the complete chaotic data file generated by the forensic laboratory's analysis of the door handle sample. Scientists would first have input the known DNA profile of Nancy Guthrie herself, obtained from a reference sample provided by her family, a cheek swab from a close relative, or a DNA sample recovered from a personal item belonging to Nancy. This known profile serves as an anchor point in the analysis, a fixed genetic reference around which the mathematical modeling can orient itself. With Nancy's profile accounted for and her contribution to the mixture mathematically modeled and subtracted, the software can begin exploring what other combinations of genetic information might explain the remaining data. Any other known profiles available from family members with documented and innocent access to the home would also be input progressively, each one reducing the genetic noise slightly and allowing the signal from the unknown contributor to become, in theory, incrementally clearer. The output of this process, if successful, is not a confirmed identity and not a clean profile ready for database searching. It is a likelihood ratio, a number expressing how much more likely the observed evidence is, under the hypothesis that a particular person was a contributor to the mixture versus the hypothesis that they were not. A likelihood ratio of 1 million means that the observed evidence is 1 million times more likely to exist if a specific person contributed to the sample than if they did not. Courts across the United States and internationally have consistently found likelihood ratios of this magnitude to be extraordinarily compelling evidence, capable of supporting a conviction when combined with other corroborating evidence. The statistical weight is, for all practical purposes, overwhelming. But there are mixture scenarios that defeat even these extraordinary programs, producing inconclusive outputs that provide no usable statistical support rather than powerfully probative likelihood ratios. A sample containing 5 or 6 contributors, with one contributor at the 10 to 15% level in a sample that has been subjected to environmental exposure over days or weeks, approaches or potentially exceeds the practical operating boundaries of current probabilistic genotyping software capability. The uncertainty becomes so large and the number of possible explanatory scenarios so vast that the software cannot converge on a probability distribution that is narrow enough to be legally meaningful. The output is, in effect, a mathematical acknowledgement that the data does not contain enough information to support a reliable statistical conclusion about any specific contributor. It is the algorithm telling investigators, honestly and precisely, that the noise in this recording is too great and the target voice too faint for this particular tool to isolate it with the confidence that the law requires. If that is what happened in the Guthrie case, and the sustained investigative silence strongly suggests that the first-line analytical approaches have not yielded a clean, actionable result. Then investigators face a choice. They can continue trying to extract more information from the mixed sample using additional computational approaches, or by revisiting the analysis with different assumptions about contributor number. Or they can look elsewhere in their evidence inventory for a different piece of biological material that might be more tractable, more amenable to the kind of analysis that could actually produce a usable result. And the reporting on this case suggests that there may be exactly such an alternative source of biological evidence available. A hair was found in Nancy Guthrie's home, and that single sentence, which might seem like a minor forensic footnote in the context of the broader investigation, may turn out to be the most important sentence in this entire story. Because what has happened to the forensic potential of a rootless hair in the last several years is one of the most remarkable scientific developments in the history of forensic DNA analysis, and it has the potential to transform this investigation completely. For the entirety of the modern forensic DNA era, spanning roughly 3 decades from the late 1980s through the mid-2010s, a rootless hair found at a crime scene was regarded by forensic scientists with a mixture of professional disappointment and pragmatic resignation. Not entirely useless, they would say, maintaining a careful optimism, because a rootless hair shaft does contain mitochondrial DNA, a form of genetic material that resides outside the cell nucleus and is inherited exclusively through the maternal line. Mitochondrial DNA analysis can establish that a hair came from a person with a particular maternal lineage, and it can potentially exclude individuals whose maternal lineage does not match. But mitochondrial DNA cannot uniquely identify an individual because it is shared identically by every person in the same maternal lineage across multiple generations. All of a woman's children, and all of their children through the female line, and all of their children in turn, share the same mitochondrial DNA sequence. As forensic identification evidence, mitochondrial DNA is a category, not a name. It can tell you that a hair came from someone within a broad population group or a specific maternal lineage, but it cannot tell you which specific individual in that lineage the hair came from. As a tool for identifying a specific unknown suspect, it has historically been of very limited value. The reason for this limitation is biological and was, until recently, considered fundamentally insurmountable. The nuclear DNA that resides in the nucleus of a living cell, the same nuclear DNA used for STR profiling and for the SNP profiling used in genetic genealogy, is simply not present in meaningful quantities in the shaft of a shed hair. The shaft of a human hair consists primarily of a structural protein called keratin, and the cells that make up the shaft are dead cells, cells that have lost their nuclei in the process of keratinization. Without a living nucleus, there is no intact nuclear DNA. A plucked hair with the root follicle cells still attached is a completely different story, because those root follicle cells are living cells with intact nuclei, but a naturally shed hair. The kind that falls out spontaneously without being pulled has no root cells attached. The shaft is all that remains, and the shaft contains only mitochondrial DNA and fragmentary, highly degraded traces of nuclear DNA that are present in quantities so small and in a condition so compromised that standard forensic analytical methods cannot work with them. This was not a methodological failing or a technology gap that better equipment could address. It was, scientists believed, a fundamental biological reality that set a hard limit on what a rootless hair could ever tell a forensic investigator. That belief, held with confidence by the forensic science community for decades, is no longer accurate. And the technology that has overturned it represents one of the most extraordinary examples of scientific cross-pollination in recent memory. A case where a methodology developed to solve one seemingly impossible problem in an entirely different field turned out to be exactly what was needed to solve an equally impossible problem in forensic science. A company called Astrea Forensics has developed and validated a methodology that changes the forensic potential of a rootless hair shaft so completely and so fundamentally that it renders the previous scientific consensus obsolete. Astrea was co-founded by Dr. Ed Green, a scientist who is renowned in the academic world not for anything related to criminal investigation, but for his extraordinary contributions to the field of ancient DNA research. Dr. Green played a central role in sequencing the Neanderthal genome, one of the most celebrated achievements in modern genomics, and in the subsequent analysis that identified the Denisovans as a distinct archaic human population, a discovery that rewrote our understanding of human evolutionary history. These achievements were made possible by the development of techniques for working with genetic material that was not merely old, but catastrophically ancient DNA that had been subjected to tens of thousands of years of chemical degradation, oxidative damage, hydrolytic fragmentation, and microbial breakdown, until it existed only as tiny, shattered pieces bearing almost no resemblance to the intact, long-stranded DNA that standard molecular biology methods require. The tools developed to recover, amplify, and interpret ancient DNA are among the most sensitive and sophisticated in all of molecular biology. They include ultra-sensitive extraction protocols that can capture genetic material present in quantities so small they would be invisible to standard methods. They include specialized library preparation techniques that can work with DNA fragments only a few dozen base pairs long, far shorter than the fragments required for standard forensic STR analysis. And they include next-generation sequencing approaches that can read millions of these tiny fragments simultaneously. And then, through sophisticated computational assembly and alignment, reconstruct the original genomic sequence from the fragmentary pieces the way an archaeologist might reconstruct a shattered ceramic vessel from 1,000 tiny shards. These techniques were developed to read the genome of a Neanderthal who died 40,000 years ago. Astrea Forensics recognized that these same techniques could be applied to a problem that was, from a technical standpoint, structurally similar, recovering usable genetic information from the shaft of a shed human hair, where the nuclear DNA, though not ancient, is present in such tiny quantities and such a fragmented state that it had always defied conventional forensic analysis. The result of successfully applying Astrea's methodology to a rootless hair shaft is not a standard STR profile because the DNA fragments recovered from the shaft are too short and too few for STR analysis, which requires longer intact template sequences to work effectively. Instead, the process produces a SNP profile, a profile based on single nucleotide polymorphisms. SNPs are positions in the genome where individual people differ from each other by a single DNA letter, an adenine where someone else has a guanine, a cytosine where someone else has a thymine. The human genome contains millions of SNP positions, and while each individual SNP carries far less identifying information than a single STR locus, a comprehensive profile based on hundreds of thousands or millions of SNPs contains an enormous amount of identifying information in aggregate, enough to distinguish any individual from any other individual on Earth with high statistical confidence, and enough to detect genetic relationships between individuals with remarkable sensitivity. More importantly for the Guthrie investigation, a SNP profile is precisely the format used by consumer genetic genealogy services. It is the format in which Ancestry DNA reports its results. It is the format used by 23andMe. It is the format accepted by GoodMatch and Family Tree DNA. It is, crucially, the format that, when uploaded to a public genealogy database, can be compared against the profiles of millions of other users to identify genetic relatives across a wide range of relationship distances. It is the format that makes investigative genetic genealogy C.C. Moore's specialty and the most powerful identification tool available to investigators working this case possible. If Astria's methodology can successfully extract a usable SNP profile from the hair found in Nancy Guthrie's home, investigators would have done something extraordinary. They would have bypassed the entire complex mixture nightmare that has been paralyzing the investigation and arrived at a clean, single-source genetic profile from a piece of evidence that the intruder almost certainly never thought about at all. A hair shed naturally, involuntarily, without any forensic awareness or any intention of leaving evidence, now carrying its owner's complete genetic identity in a format that the most advanced genealogical databases in the world can read, interpret, and use to trace that identity back to a name. The caveats must be stated clearly, because they are real and they matter. And honest reporting on forensic science requires acknowledging limitations alongside capabilities. The extraction process is irreversible. The hair shaft is physically consumed during the extraction procedure, meaning the laboratory gets exactly one attempt, and there are no second chances. If the extraction fails, or if the resulting data is too sparse or too low quality to produce a usable SNP profile, the evidence is gone permanently and irrecoverably. This is why Astria's methodology is appropriately classified as a last resort rather than a first-line approach, to be deployed only after other analytical avenues have been thoroughly explored and found insufficient. The process is also extraordinarily expensive, reflecting the sophistication of the methodology and the specialized equipment and expertise required to execute it successfully. And success is genuinely not guaranteed even under the most favorable conditions, because the quantity and integrity of nuclear DNA in a rootless hair shaft varies considerably depending on the individual, their age and health status, the portion of the hair shaft sampled, and the storage history and environmental conditions of the sample since it was collected. But when it works, and it has worked in documented forensic cases with results that have directly advanced criminal investigations, the transformation it produces is immediate and total. A door that was bricked shut by the complex mixture problem swings open entirely. The investigation that was paralyzed by an unresolvable forensic puzzle finds itself suddenly in possession of a clean, actionable genetic profile and a direct path to the most powerful identification methodology available in modern forensic science. It finds itself at the threshold of C.C. Moore's world. This is where the investigation, if the hair analysis succeeds, or if the probabilistic genotyping produces a usable result through some other avenue, shifts from the language of chemistry and molecular biology to the language of family trees, historical records, and the patient, methodical detective work of genetic genealogy. This is where C.C. Moore's specific and extraordinary expertise becomes not just relevant, but potentially decisive. Because investigative genetic genealogy, properly understood and expertly executed, is the technology that has already reached back through 30 years of silence to give Joseph James DeAngelo a name. It is the technology that produced the first ever conviction based solely on genetic genealogical identification. It is the technology that has, case by case and year by year, redrawn the map of what is possible in criminal investigation. And it is the technology that may, right now, be closing in on the person who walked out of Nancy Guthrie's home and disappeared into the Tucson night. The concept underlying investigative genetic genealogy is elegantly simple at its core, which may be one reason it took the law enforcement community as long as it did to fully recognize and embrace its potential. You take the unknown suspect's SNP profile, the same format produced by every major consumer DNA testing service, and you upload it to a genealogy database. The database searches its entire collection of user profiles for individuals who share measurable amounts of DNA with the unknown suspect, and it returns a ranked list of matches ordered by the amount of shared DNA, expressed in units called centimorgans. The centimorgan is a measure of genetic distance, and the number of centimorgans shared between two individuals is a direct and quantifiable reflection of their degree of genetic relationship. A parent and child share roughly 3,500 centimorgans. Full siblings share roughly 2,550 centimorgans on average. First cousins share roughly 850 centimorgans. Second cousins share roughly 230 centimorgans. Third cousins share roughly 75 centimorgans. Fourth cousins share roughly 35 centimorgans. To most people, a third or fourth cousin is a relationship so distant as to be practically meaningless. Most people cannot name their third cousins, much less describe them or locate them on a map. But to a skilled genetic genealogist like C.C. Moore, a third cousin match in a genealogy database is not a dead end. It is a thread. It is a specific, quantifiable genetic connection between the unknown suspect and a living, named, locatable individual who has voluntarily placed their DNA in a searchable database. And a thread, in the hands of someone who knows how to follow it with skill and persistence and deep knowledge of genealogical research methodology, can lead to a name. It has led to names before, many times, in cases far colder and far more apparently hopeless than this one. The genealogist's process begins with whatever information is publicly associated with the database match. Many people who upload their DNA to genealogy platforms also build and publish family trees, sometimes extensively documented trees tracing their ancestry back multiple generations with supporting source citations from historical records. The genealogist uses this publicly available information as a starting point, tracing the match's ancestry backward through the generations to identify the ancestral couple, the set of great-great-grandparents, or great-great-great-grandparents, who are the most likely common ancestors shared between the database match and the unknown suspect. For a third cousin relationship, that ancestral couple would typically be the match's and the suspect's shared great-great-grandparents. For a fourth cousin relationship, it would be their shared great-great-great-grandparents. Once that ancestral couple is tentatively identified, the genealogist's work shifts direction. Instead of moving backward through history toward the past, they begin moving forward, following every branch of the ancestral couple's descendant tree toward the present. Every child of that couple, every grandchild, every great-grandchild, every great-great-grandchild, all of them become part of a comprehensive and growing family tree that the genealogist is constructing in parallel with the investigative process. This forward tracing is where traditional genealogical research methodology comes into its own, and where the depth and breadth of publicly available historical records become decisive tools. Census records taken every 10 years from 1790 through 1950 and available through platforms like Ancestry.com and the National Archives provide snapshots of household composition, family relationships, ages, birthplaces, and occupations at regular intervals across American history. Birth certificates, marriage licenses, and death certificates from state vital records offices provide definitive documentation of family relationships and key life events. military service records from the Selective Service Registration Files, military personnel records, and pension files provide biographical information about a substantial fraction of the American male population across the 20th century. Local newspaper archives, increasingly digitized and searchable through platforms like newspapers.com and Chronicling America, contain obituaries that are genealogical gold mines, frequently listing the names and locations of surviving children, siblings, grandchildren, and other relatives with sufficient specificity to populate an entire generational layer of a family tree in a single document. Church records, cemetery records, local historical society archives, county histories, and city directory listings fill in the gaps that official records miss and provide additional detail about individuals and family structures at the local level. And increasingly, public social media profiles, Facebook pages, Instagram accounts, and LinkedIn profiles provide information about living individuals that allows the genealogist to begin the process of geographic and demographic filtering that transforms a large theoretical list of possible descendant names into a shorter, more focused list of plausible investigative candidates. The genealogist is not looking at this social media information to invade anyone's privacy or to make any accusation. They are simply using publicly available information to identify which descendants of the ancestral couple currently live in or have ties to the geographic area relevant to the investigation, which ones fall within the age range and demographic profile consistent with the evidence from the crime scene, and which ones might therefore warrant closer investigative attention. This process is not conducted using a single database match in isolation. One of the foundational principles of investigative genetic genealogy, as C.C. Moore practices it, is that multiple matches are worked simultaneously, with the genealogist building family trees for the top several matches on the list, and then looking for the points where those independent trees intersect with each other. This process of triangulation, as it is known in the genetic genealogy community, dramatically increases the investigator's confidence that the research is converging on the correct family and the correct ancestral couple, rather than following a false trail created by coincidental DNA sharing or database error. When 2 or 3 independently constructed family trees, built from matches on different branches of the suspect's family, all point to the same geographic region and the same small set of living descendants, that convergence is extraordinarily powerful evidence that the genealogical research has found its target. From that converged list of plausible candidates, law enforcement takes over from the genealogist. Traditional investigative techniques that have been in the law enforcement toolkit for generations are now applied to a dramatically narrowed field of suspects. Database searches, background investigations, discrete inquiries through appropriate channels, and, if necessary, physical surveillance are all brought to bear on the individuals who remain after the genealogical filtering has done its work. The list that might have started with dozens or even hundreds of theoretical descendants is progressively narrowed through the application of known investigative facts. The geographic constraints of the crime, the physical characteristics of the suspect as suggested by the security footage, behavioral patterns, and any other available intelligence, until it reaches a stage where a small number of individuals, sometimes as few as 1 or 2, remain as credible candidates for the most critical step in the entire process. That step is covert DNA collection, and it is the bridge between the probabilistic world of genealogical inference and the absolute world of direct forensic comparison. Law enforcement has broad legal authority in most jurisdictions, established through decades of Fourth Amendment jurisprudence, to collect DNA from objects that have been discarded or abandoned in public spaces by individuals of interest. A coffee cup retrieved from a trash can after a surveillance subject throws it away carries no expectation of privacy, because the subject has voluntarily abandoned it. A cigarette butt left on a public sidewalk is fair game for collection. A used straw from a fast food restaurant, a discarded tissue, a licked envelope or postage stamp. All of these are legally collectible sources of cellular material containing the individual's full DNA profile without the need for a warrant or any advance legal authorization. Law enforcement agencies across the country have developed extensive operational experience with covert DNA collection over the past decade, and the technique has been litigated and upheld in courts at every level. When the covertly collected sample is sent to the laboratory and the resulting DNA profile is compared directly to the profile recovered from the crime scene, the nature of the comparison changes fundamentally. It is no longer a probabilistic inference built on the statistical properties of distant genetic relationships and the mathematical modeling of complex mixture deconvolution. It is a direct, one-to-one forensic comparison between two profiles, one from the crime scene and one from the known individual, conducted using standard STR analysis on clean, high-quality, single-source samples. If the profiles match at all 20 caudus loci, which they will if the genealogical research has identified the correct individual, the statistical weight behind that match is overwhelming by any standard of legal proof. The phantom from Nancy Guthrie's security footage, the figure in the dark clothing and the ski mask who moved through her home with chilling purpose and vanished into the night, has a name. The investigation that appeared to be permanently stalled has its suspect, and a family that has been living through more than 2 months of agonizing uncertainty finally has the answer that justice demands. There is a fourth dimension to what Parabon Nanolabs offers that deserves specific attention in the context of this case, precisely because the intruder took such deliberate and methodical steps to conceal their physical identity. The security footage that represents one of the most significant pieces of conventional evidence in this investigation shows a figure whose face is completely hidden behind a ski mask, whose clothing provides no identifying details, and whose movements, while they reveal some information about height and general build, offer nothing that would allow a witness to recognize the individual in any conventional way. In a case where the perpetrator has so effectively neutralized the identifying power of surveillance technology, the ability to generate a physical description from a source other than visual observation becomes correspondingly more valuable. And Parabon Nanolabs has developed exactly that capability through a service called Snapshot. DNA phenotyping is the science of predicting physical appearance from genetic data, and it is built on the extensive body of genomic research conducted over the past 2 decades that has identified thousands of specific genetic variants associated with observable physical traits. Eye color, which was one of the earliest and most reliably predicted traits, can be determined from a small number of genetic variants with high accuracy. Hair color, skin pigmentation, and facial structure, which are influenced by larger numbers of genetic variants, each contributing smaller individual effects, can be predicted with lower but still meaningful accuracy. Height, facial hair patterns, freckling, and various other observable characteristics have also been associated with specific genetic variants to varying degrees of predictive reliability. Parabon's Snapshot service takes a SNP profile from a forensic sample and applies machine learning algorithms trained on large datasets of individuals with both known genetic profiles and documented physical appearances to generate probabilistic predictions of the unknown individual's physical traits across all of these dimensions simultaneously. The output of a snapshot analysis is typically a digitally rendered composite image, a computer-generated facial reconstruction that represents the algorithm's best estimate of what the unknown individual is likely to look like, synthesizing the predicted trait values into a coherent visual representation. The composite is accompanied by probability distributions for each predicted trait, expressing the algorithm's confidence level for each prediction. The analysis also includes genetic ancestry prediction, indicating the proportions of major continental ancestry groups in the individual's genetic background, and age estimation based on epigenetic markers that change in predictable ways as people age. The limitations of phenotyping must be stated honestly and prominently, because overstatement of its capabilities has been a genuine problem in some public presentations of the technology, and because accurate understanding of what it can and cannot do is essential to evaluating its investigative value appropriately. The composite images produced by Snapshot are probabilistic predictions, not portraits. They represent the average or typical appearance of someone with the predicted genetic trait profile, not necessarily the specific appearance of the actual unknown individual. Facial structure is influenced by developmental and environmental factors, including childhood nutrition, health history, and the random variation inherent in biological development that genetics does not fully or precisely determine. Cases have been documented in which Snapshot composites generated significant investigative effort focused in the wrong direction because the actual suspect's appearance differed from the predicted composite in ways that the algorithm could not anticipate from genetic data alone. Despite these real and important limitations, DNA phenotyping has proven genuinely useful in a meaningful subset of investigative contexts, particularly as a lead generation tool in cases where conventional physical description is unavailable, and as a cross-validation tool when combined with genealogical identification. In the Guthrie case, where the security footage provides only silhouette information due to the ski mask, a snapshot composite could give investigators, and potentially the public, a genetic prediction of the suspect's general appearance, a probabilistic description of eye color, hair color, skin tone, and facial structure that might trigger a recognition response in someone who knows the individual and has never connected them to the crime. Moore and her team routinely deploy phenotyping and genealogy together, using the trait predictions generated by Snapshot to cross-validate and prioritize the candidates identified through genealogical research. If the genealogical process has narrowed the suspect list to 3 individuals, and one of them has physical characteristics that align closely with the snapshot predictions while the other 2 do not, that convergence of 2 independent genetic evidence streams on the same individual builds a far stronger investigative foundation than either stream alone could offer. The ethical dimensions of all of this cannot be glossed over, because they are real, and they matter, and they are being actively debated in courts, legislative chambers, and academic ethics forums right now, even as these tools are being applied to active investigations. When a person uploads their DNA to a genealogy database, they are making a personal decision about their own genetic information. They are not, in any obvious or explicit sense, consenting to have that data used by law enforcement to navigate toward a family member as a criminal suspect. Yet that is precisely what investigative genetic genealogy does. The innocent database user becomes, without their specific awareness or consent, a waypoint in a criminal investigation. They are not suspects. They are not harmed in any direct sense. But their genetic data functions as an investigative instrument in a process they never knowingly agreed to participate in. The scale of this dynamic is what elevates it from an individual privacy concern to a societal-level policy question. Research has estimated that a law enforcement accessible genealogy database containing approximately 3 million individuals of Northern European ancestry would provide genetic coverage for roughly 60% of all people in that ancestry group through matches of third cousin or closer, meaning that roughly 60% of that population could potentially be identified through investigative genetic genealogy if they or a family member committed a crime and left DNA at the scene. As the consumer DNA testing market continues to grow, and as the fraction of tested individuals who opt into law enforcement searching potentially expands, that coverage percentage increases. The theoretical endpoint of this trajectory, if database sizes continue to grow and if access policies expand, is a de facto capability for population-level genetic identification that no legislative body has explicitly authorized and no democratic society has consciously and deliberatively chosen to create through its normal lawmaking processes. The regulatory response to this concern has been real but incomplete. The Department of Justice issued interim guidance in 2019 establishing federal policies for the use of forensic genealogy databases, requiring, among other things, that the technique be limited to violent crimes and cases involving unidentified human remains, that all other investigative leads be exhausted before the technique is deployed, and that the investigation be conducted in conjunction with a forensic DNA laboratory accredited by a recognized accrediting body. Several states, including Florida and Maryland, have passed specific legislation governing and restricting the use of genealogy databases for law enforcement purposes, requiring judicial authorization before searches can be conducted. These are meaningful regulatory steps that represent genuine efforts to establish appropriate boundaries around a powerful technology, but they are also incomplete, inconsistent across jurisdictions, and subject to revision as political and administrative priorities change. The law has not caught up with the technology, and it is not clear that the current regulatory frameworks fully capture the ethical complexity of what investigative genetic genealogy actually does. The conversation about where the appropriate boundaries lie is ongoing, vigorous, and genuinely unresolved, as it should be given the stakes involved. For the family of Nancy Guthrie, this ethical complexity exists in a context that is shaped not by philosophical abstraction, but by urgent and concrete human suffering. An 84-year-old woman is missing. She has been gone for more than 2 months. The forensic clock that governs the degradation of biological evidence is running continuously and relentlessly. DNA does not sit patiently waiting for investigators to resolve their analytical challenges. Environmental exposure, humidity, temperature variation, the invisible biological activity of microorganisms on every surface. All of these forces act on DNA samples continuously and without mercy. The intruder's contribution to the complex mixture on that door handle, already at the margins of analytical detectability when it was freshest, may have deteriorated further in the weeks since the crime. Every week that passes without a successful analysis is a week during which the evidence may be moving closer to a threshold below which reliable interpretation becomes impossible. And beyond the forensic clock is a human clock that ticks with even greater urgency. Nancy Guthrie is 84 years old. The urgency of this investigation is not abstract. It is not theoretical. It is measured in days, and those days matter in a way that no amount of procedural language can adequately convey. The investigative pipeline from the complex mixture on that door handle to a named suspect standing before a judge is a long one, and every step along it carries the possibility of failure. The probabilistic genotyping software may produce an inconclusive result if the mixture is simply too complex, and the suspect contribution too small for the algorithm to extract a reliable signal. The hair shaft may not yield a usable SNP profile if the nuclear DNA it contains is too sparse or too degraded for even Astria's advanced extraction methodology to recover. The genealogy database may not contain a match close enough to enable identification if the suspect's family has not participated in consumer DNA testing or has not opted into law enforcement searching. Each of these failure modes is real, and intellectual honesty requires acknowledging them alongside the remarkable capabilities of the technology being brought to bear. But intellectual honesty also requires acknowledging what the history of investigative genetic genealogy has demonstrated with increasing force and increasing frequency over the past 7 years. The definition of unsolvable keeps changing. Cases that were cold for 30 years and that had defeated every conventional investigative approach have been resolved. Suspects who had been living freely for decades, who had built entire lives on the foundation of their apparent forensic invisibility, have been unmasked. The biological truth that a perpetrator leaves at a crime scene, however small, however degraded, however buried in the genetic noise of innocent contributors, has proven over and over again to be more persistent and more revealing than anyone who relied on that invisibility had any reason to anticipate. Because C.C. Moore and the field she helped create have made a discipline of following the smallest threads, tracing the faintest genetic whispers back through generations of family history to the one person who should have been invisible but is not, because their biology refuses to keep their secret. The investigation into Nancy Guthrie's disappearance is not over. The silence is not surrender. It is not defeat. It is not the sound of investigators who have given up or who have run out of ideas or who have accepted that this case cannot be solved. Behind the official silence, which is itself a necessary product of the need to protect the integrity of an active investigation, the work continues with a focus and a technological sophistication that most people have never had reason to imagine. Algorithms are running their millions of simulations. Genealogists are building family trees backward through generations of historical records. Laboratories are weighing the cost and the risk and the potential reward of applying the most advanced extraction chemistry available to a single, irreplaceable hair shaft. Investigators are cross-referencing geographic and demographic data against a narrowing list of potential candidates. The machinery of modern forensic science is fully engaged, and it is more powerful today than it has ever been at any previous moment in the history of criminal investigation. Somewhere in a genealogy database, there may already be the match that opens the door. Somewhere in a historical archive, there may already be the family tree branch that leads to a name. Somewhere in a forensic laboratory, a hair shaft may be yielding, molecule by microscopic molecule, the genetic secret it has been carrying, and somewhere in Tucson or beyond, the person who walked into Nancy Guthrie's home and took her from her family may be going about their daily life with no awareness that the biology they cannot control and cannot hide is being decoded by technology. They almost certainly do not understand technology that is closing the distance between them and accountability with every passing hour. That distance may be shorter than they think. And for Nancy Guthrie's family, who have been living through a darkness that no family should ever have to endure, the possibility that it is shorter than anyone yet knows publicly represents something real and something powerful. It represents hope. Not the vague, consoling hope of people who have run out of anything concrete to say. The specific, scientifically grounded, historically validated hope of a field that has proven, again and again, in case after case and year after year, that the phantom is never as invisible as they believe, that the biology always knows, and that eventually, with the right tools and the right expertise and the relentless, focused, patient application of both, the biology always tells. If this deep dive into the science and the stakes of the Nancy Guthrie investigation gave you something new to think about, if it changed the way you see this case or opened your eyes to the extraordinary technology being deployed behind the scenes, please take a moment right now to like this video and leave a comment below. Do you believe investigators should be granted access to the larger private databases like Ancestry DNA and 23andMe in cases involving violent crimes? Where do you personally draw the line between an individual's right to genetic privacy and law enforcement's obligation to pursue justice for victims and their families? Is the potential to solve cases like this one sufficient justification for the investigative use of genealogy databases, or does the reach of the technology extend too far into the genetic privacy of innocent relatives? These questions do not have easy answers, and the fact that they do not is precisely why they deserve serious, thoughtful discussion. Drop your perspective in the comments section and let us know where you stand. And if you are not yet part of the True Crime Hex community, this is your moment to join us. Hit that subscribe button right now and ring that notification bell so that you never miss an update on the Nancy Guthrie case or any of the extraordinary and deeply important cases we cover here on this channel. We are watching this investigation with the attention and the seriousness it deserves. And when something breaks, when the silence finally cracks, and the truth that is buried in the biology finally surfaces, you will hear it here first on True Crime Hex. Thank you for watching. Thank you for caring about Nancy Guthrie and the family that is fighting every day to find her. And we will see you in the next one.